Hi everyone, welcome to this discussion session. I think this is discussion number 5. Okay. So previously we are solving current like the RL and RC circuit with current excitation, and we have just started op amp circuit like introduction of the op amp. Okay, and we have discussed these things. Okay, so let's continue from here. Okay, so we will be talking about first case ideal op amp. Okay, ideal op amp. So we have seen that for a ideal op amp, the gain is infinity, like the open loop gain is infinity, and we need a finite output impedance. Okay, and if we do negative feedback, then this these two terminal is almost equal, right? So this is called virtual short concept.
Yes,
And we have also seen that this op amp is nothing but a integrator. Okay, this op amp is nothing but a integrator. So now first thing, so and the op amp model is nothing but this. So op amp is nothing but a voltage control voltage source, and this is a actual model. Okay, actual model. So this is R in, this is V plus, this is V minus, this is plus, this is minus, this is A times V plus minus V minus, and this is our output impedance. Okay, so this is the equivalent model of a op amp. Like this is a voltage control voltage source. Okay, so ideally this output impedance is 0. Ideally this is input impedance is infinite, and ideally this gain A is infinite. Okay. Okay, so now we will be talking first about negative feedback. Okay, so negative feedback means like in our circuit there may have many disturbance like temperature disturbance, or some like what I can say, like the natural, like the disturbance from the nature. Okay, so it will hamper our circuit. Okay, in open loop configuration, so we go for the closed loop configuration and we lose our like infinite gain. Okay, to a finite gain for negative feedback, but the disturbance occurs due to some reasons. It like is controllable to us. Okay, like the all the disturbance can be like cannot affect our circuit in a much effective way. Okay, in a negative feedback circuit, but in open loop circuit, if this gain like decrease by some amount, all the circuit feel the same effect. But in the closed loop circuit, if this gain like reduced by some amount or increased by some amount, the closed loop behavior almost remains same. Okay, so this is the like this is the thing of negative feedback. Okay, so now we will be calculating a inverting and non-inverting configuration of a op amp with feedback. Okay, so let's have this circuit. So it is understandable, right? What is the negative feedback, like why we do.
yes,
So now if we normally write KCL and KVL, what will be the case? So no current can flow through this branch, right? I is 0 here, right? So all of the current flowing through this branch, and we know this node is equal to the this node, right? So now we if we apply KVL at this branch, okay, what will be the case? So this node voltage will be nothing but R1 divided by R1 plus R2 times V out, right?
Yes.
So now if we calculate V out by V in is nothing but what is the case? R1 by sorry. So
R1 plus R2 by
yes,
R1.
R1 plus R2 divided by R1, and this is nothing but 1 plus R2 by R1.
Yes.
So this gain is called closed loop gain. Okay, closed loop gain. So we can see that this is, if this like open loop gain is almost infinite, the gain is nothing but 1 plus R2 by R1. Okay, like 1 plus R2 by R1, and this is controllable to us, right? And on thing, if if this R2 and R1 varies with temperature and process and so on, but the gain is almost remain fixed, right? Because this is a ratio, so 1 plus some ratio remain a constant, right?
Yes.
Yes.
So this is the closed loop behavior. Okay, so and we are getting like much lesser gain, right? Let's R1 equals R2, so our closed loop gain is nothing but 2 here, right? So we are like, we have gain of, let's say, 80 dB, or in linear this will be 1000. So we are sacrificing our gain like from 1000 to 2. Okay, from 1000 to 2, but what we are getting, we are getting a controllable output. Okay, actually in our practical circuit we no need this type of gain. Okay, in open loop we are always go for the closed loop behavior and closed loop system, so the circuit becomes more stable, more controllable, and so on. Okay, so this configuration is called non inverting amplifier, right?
Yes.
As the input is given to the non-inverting terminal of this op-amp. Okay, and
Hmm.
the gain of a non-inverting amplifier is nothing but this. Okay, like this quantity.
1 plus R2 by R.
So in this case we are
Yes.
we denote R2 as a like this branch is called feedback network. Okay, feedback feedback network. Okay, or feedback circuit. And here we have a term called feedback factor. Okay,
Hmm.
feedback factor or feedback fraction or so on, and this is normally denoted as beta. Okay, so this is nothing but R1 divided by R1 plus R2. Okay, so this is the beta factor, and we have seen that if this is a voltage input voltage output configuration, then the closed loop gain V out of V in is nothing but 1 over beta. Okay, so this is a very good result. Okay, so if this is a voltage control voltage source, like the voltage, like the output is voltage and input is also voltage, and our
Hmm.
open loop gain is almost infinite, then our closed loop gain is nothing but the inverse of the feedback factor. Okay, and this is always true for non-inverting amplifier. Okay,
Yes. Yes.
okay, so one thing we have done. So please remember if I forget some points. Okay, Sijan.
Yes.
Okay, so now,
I think that is okay.
okay, so yes, so why we go for from open loop to closed loop, open loop to closed loop. So actually in the closed loop we have all the parameter going towards ideal behavior, right? So if we have a voltage control voltage source, so for ideal case we know that it will go to the, like if R out go below the, like what I can say, yes, so R in go to, like go towards the infinity. So this is the closed loop behavior. Like in closed loop the control voltage source go towards the ideal case. Okay, so now here one important term is loop gain. Okay, loop gain. So loop gain is nothing but the open loop gain times the feedback factor. Okay, so this is a very important term, right?
Yes.
Yes.
Yes, this is called loop gain. Okay, so how to find loop gain? So finding loop gain, what we do? We break the loop in a high impedance node. Okay, so I am finding the loop gain here. Okay, so this is our V in, and this is our network. Okay, so so we need to break the loop in a high impedance node, and we, let's say we break the loop here. Okay, and we have to apply a test voltage there, small signal test voltage there, and we have to traverse the loop and go back again to the node, and let's say the voltage is V return. Okay, then we have to take V return by V test, and this is called loop gain. Okay, right? So
Yes.
we have to
Yes.
break a high
Yes.
impedance node. So
Yes.
this is a high impedance node, right? Because the infinite, like the op amp having infinite impedance, input impedance. Okay, so I
Current is 0.
okay, I am breaking the node from here, and I will traverse the loop in this direction and go back to the node, and we'll measure V return divided by V test, and this will give our loop gain. Okay, so let's, and we have to deactivate all the independent sources. Okay, all the independent sources must be inactive, must be inactive. Inactive means if there is a current source, this will be open circuit. If there is a voltage source, this will be short circuit. So we have a like independent source of B in, so this will be short circuited to the ground, right? And let the gain is A. So now if we apply a Vt here, then what will be the voltage at this node? So V out will be nothing but A times this voltage becomes 0 here, right? So 0 minus Vt, right? So V out
Yes.
is
Yes.
minus A times Vt. Okay, right?
Yes.
And we have this V return. So this will be nothing but a voltage divider circuit. So V return, we directly write that V out times R1 divided by R1 plus R2, right? So V return will be nothing but, so V out is this. So minus times minus A times Vt times R1 divided by R1 plus R2. So we are here V return divided by Vt is nothing but minus A times R1 divided by R1 plus R2. So we can see that there is a negative sign. So this represent actually our negative feedback. Okay.
Yes. Yes.
If the loop gain having negative sign, this ensures our the circuit having in negative feedback. Okay. And we can see that. So this is A, and this will be our beta, right? We have calculated this one, right? So this is how we can find the loop gain. So gain loop gain is A times beta. So this is minus. Okay. So actually I was telling, if we have a negative feedback circuit, the control sources go towards ideal. Okay, so now we know that uh, what will be the R in here. So let's say R in closed loop. So R in closed loop will be nothing but, so ideally it should be infinite, right?
Yes.
Yes.
So this will be, let's say the, so okay, let me do here. So let's say this is R in open loop. Okay, and this is RO open loop. Okay, now if we write KCL and KVLs and try to solve this circuit, the R in closed loop will be nothing but R in open loop times 1 plus A beta. Okay, so so this, if A is like finite, but total input impedance is going towards infinity, right? So this is the ideal case, right? Like if
Yes.
you
Yes.
want a like voltage control voltage source must have a higher input impedance. So actually, and we know that A beta plus A. So if A beta is much greater than 1, so this is simply A beta, right? So we generally say, so the closed loop input impedance is multiplied with the loop gain itself. Okay, like loop gain times the open loop impedance. Okay.
Yes.
Okay, then what will be the R out closed loop? So we know that the ideally the voltage control voltage source, the output impedance will be 0. So if we have a open loop R out, let's say open loop, so this will be reduced by the loop gain. Okay, so this will be nothing but this 1 plus A beta. So this will be nothing but RO open loop divided by loop gain. Okay, so the closed loop input impedance output impedance is reduced by the loop gain factor. Okay, so the
Yes.
so our circuit becomes more ideal voltage control voltage source. Okay, so this is, let's say, RO closed loop. This value is this, and let's say this is R in closed loop. So this voltage is like this, quantity is this. Okay, so this is how negative feedback works in our real circuits. Okay,
Yes.
now what we should discuss, Sijan? Okay,
So
okay, we
here
should discuss
the
like
loop gain is,
inverting configuration, right?
yes.
Okay, so we have discussed previously non-inverting configuration. Now is inverting amplifier.
With the same topology we should discuss,
Yes, with
I
the
think.
same topology. So our topology will be same, and there is a feedback, negative feedback, right? Feedback always be negative. Okay, so it can act as a amplifier. If there is a positive feedback, it will try to oscillate. Okay, it will not be a amplifier anymore. Okay,
Yes.
if there is a positive feedback.
Yes.
So where we should give the input here, right?
At, yes, at the non-inverting terminal. Inverting
Yes,
terminal. Yes.
inverting term. So
Invert.
this is V in, right?
Yes, yes.
Yes.
Now if we try to solve, is this circuit okay? Hello.
Yes. Yes.
Now what will be the gain? V out by V in.
R1. R1 by R2 plus R1.
Sure.
This is a inverting amplifier. So this is minus R1 by R2.
Basically, this is not the actual circuit. Okay, this is wrong. Why wrong?
Yes.
Because this is virtually shorted, but this is not possible, right? This is ground, this is win, this is not okay. So the circuit is the following. Okay, actually I
Yes.
intentionally make it wrong. So let make it. So this is the circuit. Okay, right?
Hmm.
Here is the V. Previously the V was at this terminal. Okay, but actually this should be in this terminal. Okay, input. Okay, hello.
Yes, yes.
Ha.
Okay, so now if this is infinite ideal case, what should be the gain? So we can see that this node will be also grounded, right? So
Yes.
a constant current is flowing through this path. If this V in is constant, so this current has to
Yes.
flow through this path. So if we write KCL or KVL, so what we can do? So this current is equal to this current. So V in minus 0 divided by R1 will be equal to 0 minus V out divided by R2. So V out by
Yes.
V in will be nothing but minus R2
R2
by
by R.
R2 by
R1.
R1.
So this is the closed loop gain. Okay, and we can see there is a negative sign. This negative signs,
Yes.
what does it mean? This means the input is applied in the inverting terminal.
Inverting terminal.
Okay, not for the loop gain case. Okay, the negative feedback case. For negative feedback case, we have to find the loop gain. Okay, but in this circuit, finding the loop gain is not so easy, because here the output is voltage and the feedback component is current. Okay, so we no need to do that. We will discuss this circuit in a deep way in some another video. Okay,
Yes.
okay, okay. So now, and we can see that previously, if when we have a non-inverting configuration, we have the positive output, right? Okay, let me uh, so what was the output? 1 plus, yes. So here we have the positive output, right? So this is ensures the input is applied in the non-inverting terminal. Okay, and here this sign indicates the input is applied in the inverting terminal. Okay, so this is the case. So okay, uh, so okay, so now Sijan, we should go for the adder circuit, right?
Yes.
Or should I mention some other things? Okay, let me do. Okay, so here on current is flowing and no current can goes through this branch. Okay, so we can write these things, right? Because the input impedance is so
Yes.
high, no current can go through these branches. Okay, so that we can
Can I can
directly
I
say,
can I write loop gain for this circuit?
bolo, yes,
Can I write loop gain for this
yes,
circuit?
yes, we can write. Okay, let me try to make loop gain here. Okay, so we have to cut, but here you will find a magic. Okay, so I was telling we will discuss in another video. Okay, so if you ask, so let's do. So this will be short circuit, right, for finding loop gain, and we have
Yes.
to apply a VT here, test voltage, and we have to traverse the loop and find the voltage here. This is the V return, right,
Yes.
Priyanka? Okay, so now if we traverse the loop, so what will be the V out here? So V out will be nothing but, so here this is grounded, so this will be nothing but VT minus of A, right? This V out voltage,
Yes.
and V return will be nothing but a normal voltage divider. So this will be nothing but V out into R1 divided by R1 plus R2.
Yes.
And one thing, loop gain is always be unitless. Okay, loop gain is always unitless. Okay, loop gain is always unitless. Mind it. So now, so okay, V out is nothing but minus VT into A times R1 divided by R1 plus R2. So here V return by Vt is minus A times R1 divided by R1 plus R2, right? So this is the loop gain. Actually, the loop gain I think remains same, right, Sijan? For the non-inverting case.
Yes.
Yes.
But
Yes.
yes, but here we cannot directly say the V out over V in is in like direct inversely over inverse of this beta, because the beta here not this case. Okay, okay. So we will discuss this circuit in later videos. Okay,
Okay.
because what we have seen that the gain is nothing but minus R2 by R1, right? Now if we do inverse of this will be nothing but R1 plus R2 divided by R1. So this is not the same thing like to minus R2 by R1, right?
Yes.
So that I have said that, so we will discuss it in later video. So basically this is a trivial circuit. Okay, to write
Yes.
like
Here
the
the feedback factor beta changes from the
yes,
previous
yes,
circuit.
yes, yes. So this is the thing. Okay, basically this becomes a TIA, trans impedance amplifier. Okay,
Yes.
but we know that the voltage control, like the op amp is a voltage control voltage source. Okay, like the voltage amplifier we can say, but in this case it becomes TIA, trans impedance amplifier. Okay,
Okay.
right, right. Okay, now okay, let have a adder circuit. Okay, adder means, so we have, let's say we have we have to add some different type of voltage, like let's say we have V1, we have V2, we have V3 and so on, and we want a function that can add voltages of V1 plus V2 plus V3, right? So using op amp we can do that, right, Sijan?
Yes.
Okay, let's have it. So So this is the circuit. Actually we need negative feedback all the time. Okay, this is the one thing you should mind. So
Yes.
let's plus here and minus here. So for negative feedback we have this. Now how to give the different types of input? Like we need all the positive case. Okay, so this will be plus. Okay, now we have to give the input like this, right Sijan? Sijan?
Yeah, yeah.
Right, so now we have to do it now superposition only. Okay, so for superposition what we can do? So first let's say v1 is active only and v2 and v3 is inactive, so this will be short circuited to the ground, right?
Yes.
Now what is the voltage at this node? V plus?
It's only V1.
No, 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 this is the wrong. So I want to discuss it. Yes, because in this circuit the circuit becomes the following. Okay, let me copy this. Now this circuit becomes this. Now this will make a closed circuit na, so this will be a voltage divider in the here. So v plus will be nothing but ry parallel rz, sorry, divided by ry parallel rz plus rx times v1, right?
V1. Okay.
Right na? Now what will be the v out? So v out will be nothing but this vt, like v plus, this v plus times, so this is a inverting amplifier, right? Like non-inverting configuration, so we know that
Yes, yes.
gain is nothing but 1 plus r2 by r1, right?
Yes.
Okay, okay, let me go to
I think there is some confusion here.
okay, 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 let me check, let me do this. So what was our v out here? V out was 1 plus R2 by R1 times this inverting amplifier, like non-inverting voltage, right? This is nothing but V plus or the V in, you can say, right?
Yes.
So I write there, write it here, writing here. Okay. So this is the case. So the voltage here will be multiplied with 1 plus R2 by R1. Is there any confusion still there?
Shouldn't we give the input to the inverting terminal?
Here.
Yes. You
So then
get the
you
V1, V2, V3 in the non-inverting terminal.
huh?
So shouldn't we give at the inverting terminal to get the other expression?
I can't get you again, please. Again, can't.
You have given the V1, V2, V3 in the non-inverting terminal,
Yes, yes,
right? So if we do the V1, V2, V3 in the inverting terminal,
yes,
so don't we get the adder expression for
yes. We
this
will
case?
get the adder expression, but with a negative side. Okay, we will get the
Okay.
same thing, but with a 180-degree phase shift. nothing else.
Yes.
Okay.
So can you draw it beside
Yes,
of
yes.
this
So let
picture?
me finish it. Okay. So I have
Okay. Okay.
I
Okay.
I just do for this V on sources, right? We have to do for all of the above, right? So we can see that every case, this term will be multiplied with this node voltage, right?
Yes. Yes. One
So
plus
we
R2
can,
Y around.
yes, so we can directly write that. So we can directly write. So this term will be different in each case, right? Like the V positive. So we can see that
Yes.
for when V2 is active, the VB active only, then the V plus will be nothing but, so this is active now and these two are grounded. Okay. So these two comes in parallel, Rx and Rz. So Rx parallel Rz divided by Rx parallel Rz plus Ry times V2, right?
Yes.
So I am not going to write the next one. So I will directly write the output expression. So V out will be nothing but so this will be okay. Let me, so R Ry parallel Rz divided by Ry parallel Rz plus Rx times V in plus Rx parallel Rz divided by Rx parallel Rz plus Ry times V2, right? Plus Ry, sorry, Rx parallel Ry divided by Rx parallel Ry plus Rz times V3, right? Into whole
Yes.
multiplied by 1 plus this thing, right? 1
Hmm.
plus
Yes.
R2 by R1. Okay. So actually our magnitude is modified somehow, but we are getting the nature of this V out will be addition of this 3 voltage, right? And we can scale these terms, this term, this terms, this term according to our requirement, right? But the nature of the waveform will be the addition of these three waveform, V1, V2 and V3. Okay.
Yeah. Okay.
Okay. So now coming to second case, Sijon was asking if we do that. So now if we have this case, Sijon, this is the picture, right?
Yes. Yes.
So now it will be having same superposition combination, but there will be a negative sign of minus R2 by okay. So okay, let me do that. Okay, so this will, when V1 is only active, so this will be short circuited to the ground, right?
Yes.
So okay, let me do. So now once again, so if this is ground and virtually this node is also ground, na,
Yes.
so basically this branch is out of the picture.
Yes. These have no effect on the
Okay, so
resistance.
the normally the V out by V in becomes so this will be R2 by Rx times V1 minus R2 by
Yes.
Ry times V2 minus
V2. Yes. Yes.
R3 sorry, R2 by Rz times V3. Okay, so there is I have told now, so there will be only negative sign. Okay, so this can be R2 is common, V1 by Rx plus V2 by Ry plus V3 by Rz. Okay,
Yes.
and we can like scaling down with this term and this term, but the wave nature of the V out waveform will be the addition of this V1, V2 and V3. Okay.
Yes. Yes. If we make R2 is equals to Rx Ry as it, then it is a pure addition
Then
of
it will
V1
be
P2 V3.
normally the minus of V1 plus V2 and V3. Yes.
Yes.
Okay. Now what should I do next? So inverting, non-inverting, and adder circuits are done. Okay, and for yeah, like if we do subtractor circuit, so you can apply a voltage there and another voltage there, so it will subtract. Okay, so I am not going to do that, right, Sijan? If we have a like,
Yes, yes,
if you want to subtract and subtract an waveform from another waveform, so we can directly apply two different input from two different terminal, so it will subtract.
yes, yes,
Basically op amp is a subtractor with a high gain, right?
yes,
Right, op amp is a subtractor with a high gain. So now can we go for like op amp indicator?
yes, yes, of
Like the
course.
op amp indicator is the like one of the most thing in our circuits. Okay, in our indicator circuit, op
Yes,
amp indicator. Okay, so now, okay, so we are going to do op amp indicator and op amp differentiator today, and then from next class we will try to uh, like we will try to go for the op amp frequency responses and non-ideality of the op amp, like the offset voltage, offset current, and so on. Okay,
yes, yes.
okay, now go for a
Good.
op amp indicator circuit. And for a op amp indicator circuit, I will discuss a interesting problem, and that is frequently asked in your interview. Okay, so let's do that. So let's we have an ideal op amp. So for indicator, we need a capacitor always, right?
Yes,
And we have a resistance. So actually, we if we need indicator, so capacitor integrate the current, right? And inductor integrates the voltage. So we are going to do
yes,
with a capacitor. Like this is a more common and more practically used circuit. Okay.
yes,
So this is our V in. This is our A. So why we call this is a indicator circuit? So actually we will write some KCL and KVLs, or in Laplace domain analysis we will see the V out is the integrating function of this input. Okay. So let's do that. How we can go?
make make A is equals to very high.
Yes. Sorry. So this is very high. So actually this node is equal to this node, so this will be grounded. So we can see that this single current is flowing through this whole path, right?
Yes,
So what is the current here? So let's say IC. So IC means like the same current, na? IC equal to IR is nothing but V in minus 0 divided by R. So this is nothing but V
yes,
in by R, right?
exactly.
Yes. Now this current is flowing through the capacitor. Then what is the voltage developed across this capacitor? VC. So VC is nothing but integration of, or like 1 by C integration of IC times dt, right?
Yes,
Priyanka, okay?
Yes, yes.
Yes. So the current is flowing in the path. So this terminal will be positive and this terminal will be negative, right? Now what is the V out? So we can see that, and we can also see that VC is nothing but this potential minus this potential, right? So this is potential is 0 minus this potential is V out, right?
yes,
Yes.
So now, so okay, so now we can see that V out will be nothing but minus of 1 by C. So I will put IC value. So this is V in by R and this is dt, right? So we can see that V out is nothing but minus 1 by RC integration V in dt. So we can see that V out is a function, like the integration function of this V in with respect to time, right?
Yes.
So that it is called a integrator. Understood?
Yes.
yes.
This mathematical explanation. What is the physical explanation?
Not in the
What is the physical explanation? This is the mathematical.
Yes, physical expression we all know, na. The capacitor is always indicate the current. This is the like the physical thing, na. Like if the current is increasing, then the voltage develop across the capacitor will be increasing. So this is the physical significance we
Yes,
can see. Okay, we all know, but we are trying to do with a op amp, and let's check this circuit is actually giving our required indication or not. Okay, so this is the thing. So if our
Yes.
let's say input is sine omega t, so it will give a cos, right?
yes,
So this is the physical things.
I think, Amit, the more physical explanation will be given if we give a pulse input in this.
Yeah, yes,
So
yes. So
we
basically,
we
so
can
if
see
this is
the
a pulse,
integration operation in this.
yes. So if this is a pulse, right? So the capacitor, the voltage across the capacitor is always like this, right?
yes,
So
yes,
this is the physical things. The capacitor integrates means key. Integrate means it adds its previous voltage with the present. So you all know
Yes.
that the capacitor does this. Okay, okay. So now,
yes.
okay, let have a interesting problem, and this question is like frequently asked, and it will build your intuition so like in a deep way. Okay, I will try. I will like encourage you to do it with me. Okay,
Sure.
same circuit, same cases, and we have, let's say, 5 volt minus 5 volts. Okay, and we know that the op amp output cannot be higher than the plus VCC and cannot be lower than minus VCC. We all know that, right?
Yes,
Yes.
Now I need, so let's say if V in is a pulse, like a step. Okay, let's say step of 1 volt. Okay, I need the waveform of this node, the voltage across the capacitor, and the output, and the current through the capacitor. We need this 4 plot. Okay, let's do. Now I will ask a question. How can we go to the solution? What will be your approach? We need 4 parameters. Okay, so let's say this is V out versus time. Let's say V plus versus time. Let's say this is VC versus time, and let's say this is IC versus time. Okay, so we need 4 plots. Now how can we go for the solution season? And the op amp is ideal of gain infinity. Anyone?
And the capacitor is uncharged
Yeah,
previously.
yes, the capacitor, whenever there is no initial condition mentioned, always assume capacitor is initially uncharged. Okay,
Yes. Yes. Okay.
okay. So anyone, like the what would be your first approach for your solution? So first thing we can see that this is a negative feedback circuit. Okay, if there is a negative feedback circuit, always try to go and check the virtual short concept can be applied or not. Okay, so first thing we have to see, for op amp based negative feedback circuit, we have to check is there is negative feedback or not. Okay,
Okay.
so we can directly see that there is a negative feedback present. Okay, there is no doubt. Okay,
yes,
now check if the op amp is saturated or not. So we can see that the op amp is not saturated. Okay,
Yes.
Like the v, if the v out is nothing, like we can always assume the v out is 0 initially. Okay.
Yes.
And third thing is the gain is the op amp is ideal or not. So ideal op amp means the gain is infinite here. Okay. So if these three condition is satisfied, only then we can apply virtual short concept. Okay, understood? Virtual concept short can be applied if these three things is meeting simultaneously, like at the same time. Okay. So here in this case, the feedback is negative, the op amp is not saturated, and the ideal op amp. So we can directly use the virtual short concept. So if the virtual short concept is applied, so these voltages go to ground, right? 0 volt. Now what is the next approach? So we can see that if this is ground and this is a constant voltage, so there is a constant current, right?
Yes.
Hello.
Yes.
So if there is a constant current, no current can go through this branch. So all of the current has to go through this capacitor, and the
Capacitor.
IC
Yes.
is also constant, right?
Yes.
So the if the current through a capacitor is constant, so the voltage across the capacitor will be ramping up, right? Right?
Yes.
Yes.
The voltage across the capacitor will be ramping up, and this voltage will be plus and this voltage will be minus, like the this terminal will be positive and this terminal will be negative, right?
Yes.
Yes.
Now so low, so how do we have find that? So we have find that this and okay, one thing let me do. So if this voltage is going to increase, this voltage is going to increase, what will be the this voltage? Like
The
what
question again, please.
VC is nothing but 0 minus V out, na? This voltage is 0.
Yes.
So if this voltage is ramping up, then what should be this voltage?
V
V
out
out
will
will be
increase.
minus of VC, na? So this will be ramping down like this,
Oh,
right?
Yes. Yes.
V out is nothing but minus of VC. This voltage is rising up. Another thing, another intuition I am giving to you. This node potential is we making deliberately to 0, and a positive current is flowing through this path. So this node will be positive and this node will be negative, but this node is like intentionally we are making 0. So if this voltage is positive, so this voltage must be negative, so that this terminal positive become positive and this terminal become negative, right? So this voltage, this
Yes.
node
Yes.
voltage becomes negative, right? Understood?
yes. Yes.
Like this node normally will be more negative than this node. This is the thing. This node potential will be more negative than this node potential, so that the VC is going to charge, like the voltage at the capacitor is increasing, right? So what we have seen that the V out is going to decrease linearly. V plus is always fixed to 0 voltage, and V out is also going to ramping up. And what is the I is constant, right? IC is constant, na?
Yes.
This is a
Yes.
constant
Yes.
current.
Yes.
Let's say this is a some time tx. Okay, this is the time tx. Let's say this is tx, this is tx, this is tx, this is it. So now how much the output can go? So this can go to -5, right? Maximum.
Yes. Yes.
Yes. -5.
So now
Negative
this
feedback.
this voltage is +5, and this current is nothing but 1 volt divided by R. This is clear, right? Sijan?
Yes.
Say it
Now,
again.
yes.
I don't get it.
Okay. So how much the output can go? It can go
Negative
maximum
is it?
5, right?
Yes,
Negative
yes,
5, negative 5, minus 5, right?
yes,
Yes.
Then the VC at Tx will be plus 5, right?
yes, yes,
Yes. Yes.
And the IC at Tx will be nothing but 1 volt divided by R, right? As the V plus is 0 volt, this is 0 volt, right? Up to that, okay?
yes.
Now, what the circuit will behave? Can anyone comment? Anyone? Now the circuit is saturated, right? The op amp is
Yes,
saturated.
yes.
V out
Yes,
is
open
saturated.
is saturated.
So the
Yes,
output will
virtual.
remain minus 5 for his entire life.
Yes,
Okay. So now the virtual short concept is valid? No. After Tx,
virtual
virtual short concept is not valid
is not
because
considered.
this
Yes,
is this is not meeting, right?
yes.
So now what will be the circuit? So let me draw the circuit again. This is after T equals Tx plus. Okay. Now virtual ground short is not possible here. Now V out is saturated to minus 5, right?
Yes.
Now what will be the circuit behavior? This node potential no more 0 volt, okay? And the op amp is saturated to minus 5 volt. Now actually what op amp will do? Op amp will stop its working, okay? Op amp is dead right now, okay? Then the equivalent picture will be normal RC circuit. Get it or not?
Yes.
So op amp is not working. So the picture will be looking like this, right?
Yes.
If I remove, if I cut this block, so this will like will be looking like the following, right? Now, what do you think? What will be the V plus and the
Yes.
VC and the IC? So this is IC. This is a normal RC filter, na? So please tell how much this node potential can go. V plus. Tell at steady state what will be the case? Please tell, please.
Frequency is 0
Huh?
and so impedance is high.
Yes. Then what will be the
So it is
state?
open circuit.
Yes, open circuit. Okay. So what is the V plus at steady state?
So it is V in.
Yes, it is V in, right? And what will be the nature of this graph? This will be always a exponential. We all know, right? This is a normal RC filter or RC integrator, whatever you can say, right?
Yes,
So now V plus terminal will increase exponentially to 1 volt. Okay, clear?
yes,
Now what will be the VC? VC is nothing but V plus minus V out, right?
yes,
Yes.
VC is nothing but VC minus it, this like V out, and V out is minus 5 volt. This is fixed. So VC will be nothing but V plus 5 volt, right? So this will
yes.
Yes.
be 1 plus 5. So this will be 6.
6.
So VC will try to go up to 6 volts exponentially. Understood?
Yes.
This is linear up to that, and this is exponential. Okay. Now what about IC? What is the IC at steady state?
Correct. Mm,
What
it
is the IC
is
at steady state?
0.
Zero, na? Now the question is, so we have seen that the IC becomes zero at steady state. So let's say this is zero. Now the question is how it go down from 1 V by R to 0 volt. What will be the nature at this time duration? This is always exponential. Now we all know from the basics, right?
Yes.
So this is the final waveforms of these 4 parameters. Okay, this is a very important circuit. You can feel it, right?
Yes. It is very tough.
Yes, this is very interesting circuit as well. Okay, so now how much time we are left? So okay, let me introduce. Let me introduce the op-amp differentiator circuit. Okay, actually we are doing all the ideal differentiator, ideal indicator. Okay, now what will be the block diagram of a ideal indicator differentiator?
So if the VC changes,
Yes, yes. If
what
the
is the change in V out?
season
If
again,
VC changes, what
VC
is the change in V out after time Tx?
after time tx, yes, then
What is the change in V out?
V out is not changing, na? V out is already saturated to minus 5 volt.
So after Tx, the op amp will work or not?
Not working, na? So that I have making this type of modification, na? Op amp is not working anymore.
So is VC and VR changes like this?
Again I can't get it. Which
If op amp doesn't work, VC and VR changes like this. Is it okay?
VC and VR?
After time Tx,
Huh?
VC is constant after Tx, that is 6 volt.
Now after TX, no. This is not after TX. It is let's say TY time. Okay. After TY time, the like all the things happen. It goes to steady state at TY. Okay.
so why it is not in steady state at Tx?
It cannot go to steady state, na? There is 1 volt present there, and it needs time to charge up to another 1 volt to the
Yeah.
capacitor, right?
Yes. Time is needed.
After TX plus time, the circuit becomes looking like this, na? So it will take time to reach the voltage here. We all know, na,
Okay.
Some
Sijan?
delay is
we
there.
we all
Like,
know, na? So if this is our circuit, it takes some time to take this voltage V in, right?
kind of delay.
Yes, RC is always a delay, na? Time constant. What is time constant? This is a delay,
Yes.
na?
Yes. Yes.
And almost
Yes.
the TX is nothing but 5 times RC. We all know that, right?
Yes.
Actually, Sijan, think like this. The capacitor is initially charged to like this. Then it takes, understood? So it is charged to this voltage, na? 5 volt, na?
Okay.
it
Okay.
it is initially charged to 5 volt. from here to there. So the initially the VC of let's say Tx plus Tx minus was 5 volt. Huh? The capacitor was initially charged.
Yes.
If we consider amount T equals to Tx plus. Okay. Understood, I think.
Okay. Okay.
Actually, this is a very trivial circuit. Actually, I encourage you to do it by your end. Okay. Like at least once.
Yes. Of course.
So now differentiator is nothing but the output is taken across the resistance. Bas. This is the difference. Right? So again, we can do the like
Yes.
normal KCL and KVLs. So we can see that there is a only one current flowing through in this path, right? IC. As no current can go through this op-amp terminals, right? And this voltage is grounded due to the virtual short concept, right?
Yes.
So now, so this current, what will be this current? This current is nothing but IC is nothing but 0 minus V out divided by R, right? Right?
Hmm.
And this current is flowing through this capacitor. Then the voltage drop across the capacitor VC is nothing but V in minus 0, right? And this will be
Yes.
nothing but 1 over C integration minus V out by R into dt, right?
Yes.
Equal to V in, right? So now if we do, so this will be nothing but minus 1 by RC V out differentiation of V in, right? Right?
Yes.
Srijan, it is okay?
Yes. Yes.
So actually, as this is a differentiator, we can see that the output is a function of the differentiator of input with respect to time, right?
Yes.
Yes.
Okay. So mm, so dif so okay. So let's stop here and we will discuss from next class this differentiator circuit. Okay. Hello. Hello.
Okay.
Thanks.